Hello everyone, welcome to the third part on the discussion of slope deflection method. So if you missed to watch the first two parts of this topic, I have posted the link in the description below. So by the way, I am Engineer J, currently teaching, and I'm also a civil engineer by profession. So I have this topic, or this third part on the discussion of slope deflection method. If you have watched my first two parts, so I have discussed about the equation that we used in solving the slope deflection method. I have also introduced the modified slope deflection equation. And then we tried to apply those equations in analyzing indeterminate beam structure. But in this video, we will try to use those equations in analyzing frame structure. Okay, so again, this video will focus more on the analysis of frame structure. Now, in analyzing frame, we have two different cases. We have frame without sideways, and we have also frame with sideways. As what you can see here, we have frame without sideways. So for the frame which is being restricted to move horizontally, just like this one, as what you can see, we have a hinged point, or we have a hinge support on the leftmost, and that hinge there restricts our frame to have a sideways. And also, if our frame is symmetrical with respect to y-axis, just like this one here, and we know that due to its symmetrical form, there would also no horizontal settlement of the joint in our frame system, and thus we have no sideways to this type of frame system. But for this frame structure in which we have a horizontal component of load P, that horizontal component of that load would deflect our frame like this one here. Because what you can see, we have a rotation or chord rotation of member AD and chord rotation of member BE. Hence, this is an example of a frame with sideways. So therefore, to summarize, sideways will only occur if our frame is asymmetrical, or if there is a horizontal load that acts laterally on the frame system. Okay, so but in this video we will only try to solve a frame without sideways. So basically, the equation that we will be using is the same as with the beam, as what I have mentioned, as what I have presented in my previous videos. But for frame with sideways, we will be using the value of R, in which we have delta over A, because as we all know, R here denotes chord rotation. Okay, so we have this example. So this example of a simple frame in which we have a 50 kilonewton per meter load that runs from C to E, and we have a horizontal concentrated load that acts at point B. This is an example of a frame without a sideways, because our frame here is being restricted to have a settlement in horizontal direction, because we have support C here. Okay, that restricts the movement of our frame to move horizontally. So our goal here is to compute for the reactions. Okay, so as what you can see, this is an example of indeterminate structure, because we have a two support, and we can't apply the equilibrium equations to solve these unknowns. So we have two supports and a total of 4 external reactions. We have here, of course, we have CY, CX, and AY, AX. So we can divide this frame structure into 3. We have a CD, DE, and DA. So we begin at member CD. So we have this free body diagram in which we have the uniformly distributed load, 50 kilonewton per meter. This is our C and this is our D. And then we have the reaction CY and the reaction of left of D. okay, or RDL. Then we have moment here, we have MCD, and we have here MDC. So again, our goal here is to create a slope deflection equation for both members. But MCD is equal to 0 because again, this is a hinge support. So therefore, according to what I have discussed in the second part of this video, if our MCD is equal to 0, then we can use the modified slope equation for MDC. Okay, the modified slope deflection equation, in which we can say that since MCD is equal to 0, then we have MDC is equal to, we have the formula 3EI over L times theta D minus R, plus we have the fixed end moment DC minus the fixed end moment CD over 2. Okay, so this equation is only applicable if the moment of the right or left support is 0. So we have 3E. Now take note, the moment of inertia of member CD is twice the moment of inertia for DA. So from the figure, we have CD and DE as twice the moment of inertia of DA. Okay, that means we will be using that value. We have 2I over the length is 4 meters, times theta D. Now again, we do not have chord rotation because we do not have a sideways unsettlement on our frame system. So we let R is equal to 0. Then plus the fixed end moment DC. Now in our in the first part of this discussion, I have presented the formula for fixed end moment, that if we have uniformly distributed load all throughout the beam, if we have this restrained beam which has a 2 fixed support, and this uniformly distributed load has a magnitude of W, and the fixed end moment on the left support is WL squared over 12. This is positive because we assume that as counterclockwise, and on the right support is negative WL squared over 12. Therefore, for the fixed end moment of CD, we have W 50 times 4 squared, that's L over 12, and this equals to 66.667. Now for fixed end moment of DC, this is just negative of the value. We have negative 66.667. So we substitute this value to the equation. We have FEMDC. We have negative 66.667. This is in kilonewton meter. Minus FEMCD, we have 66.667 over 2. So therefore, we have our MDC here is equal to, we have a 3 over 2 EI theta D, then minus 100. So this is now our first equation. We will go back to this equation later on after we are done with the computation of, or the generation of the other moment slope deflection equation. And now for MDE, we have this free body diagram. This is overhang, so therefore we can just apply the equilibrium equation here, in which this is our moment. Let's say it's our MDE. The length is 1 meters, and we have 50 kilonewton per meter. Okay, so we have this reaction. We have the R, D, R. Okay, so the same as with this free body diagram, we have here the R, D, L, and here we have the RC. So to compute, of course, for MDE, we can just sum up moment at D is equal to 0, counterclockwise positive. Then we have MDE minus 50 times 1 times 0.5, and this equals to 0. So we have MDE here, which is equal to 25 kilonewton a meter. So we have solved MDE now. So this could be helpful, especially when we will be creating joint condition later on. And now let's proceed to the column. We have DA, okay, and we have the 75 kilonewton concentrated load, which acts 1 meter from A and 2 meters from D. Okay, and at A, since this is a hinge, we have two values. We have RAY and we have also RAX. And at point D, we have R, D, let's say this a C, because we have the left, the right, and now let's make it a C, or the center. Then we have the horizontal, RDX, and of course the moment. So we can express this as like this beam here. We have 75 kilonewton, this is 1 meter, and this is 2 meters. So we have this moment here which is counterclockwise. So therefore, on this side we have counterclockwise. This is MDA, and then on this side we have clockwise. It's MAD. So we have here MAD. However, guys, our MAD here is equal to 0 because we have hinged at point A. So therefore, we can use the modified slope deflection method or equation on MDA. So we have MDA is equal to, we have a 3EI over L times, we have a theta A, theta D minus R, okay, plus the fixed end moment of DA minus the fixed end moment AD over 2. Okay, so this is the modified slope deflection equation. So we have MDA is equal to 3E. Our I here is I alone, so this is I over L. We have a 3 times theta D. We do not have settlement of support, plus the fixed end moment. So again, if this is our restricted beam or restrained beam, we have load P here, which is 75. So our fixed end moment DA here is equal to, now again, if this is 1 and this is 2, is equal to, now we use the formula PAB squared over L squared. So we have P 75, A here is 2, B is 1 squared, or the farthest from the leftmost support. We have 3 squared, and this equals to 16.667 kilonewton meters. And then we have here the fixed end moment for AD. So we use the formula P A squared B over L squared. Okay, I have presented the formula for fixed end moment on the first part of this discussion. So we have 75 times 2 squared times 1 over 3 squared. So we have 33.333 kilonewton a meter, and we set this one as negative because this rotates clockwise. So we have the value of FEMDA, the fixed moment DA, which is 16.667 minus, we have the negative 33.333 over 2. Okay, so by further simplifying, we have MDA equals to, we have theta D EI plus 33.333. Okay, so this is now our equation number 2. And so we tabulate all the equation. Okay, so we have the previously computed one. We have the MDC, which is equal to 3 over 2. Okay, we have EI theta D minus 100. And we can actually again express this one as a single variable. We can express that as theta prime D. And lastly, we have MDA is equal to, we have EI theta D, so we can just express that as EI, or that is theta prime D, plus 33.333. So this is our first and second equation. But take note, we have three unknowns. We have theta prime D, we have theta, we have MDC, and lastly we have MDA. So we will be needing another equation that would suffice the number of unknowns. But where to extract the third equation? Now, looking at this figure, as what you can see, we have equilibrium at point D. Again, we have three moments at point D. We have MDC, we have MDE, and we have moment MDA. Okay? Now, since these are in equilibrium, therefore, we can say that if we add these three moments, MDC plus MDA and MDE, this should give us 0 moment. Okay? But we have already computed MDE, and we know that MDE here is 25, and that rotates counterclockwise. That means that is positive. So that is positive at 25 kilonewton a meter. We have already computed this one by just using the equilibrium equation. So therefore, our third equation is we have MDC plus MDA, then you add a positive 25, that is for MDE, and this equals to 0. So therefore, this could be our third equation. So we have MDC plus MDA equals to negative 25. Okay? Now, we can substitute the equation MDC and MDA. So we have 3 over 2 theta prime D minus 100. So this is our MDC, plus we have a theta prime D plus 33.333, and this equals to negative 25. So we have theta prime D here, which is equal to 16.667. And again, this is not the slope, because to compute for the exact slope, theta D, you just need to divide it by EI. So 16.667 kilonewton meter squared over EI. So this is now the value of theta D, or theta prime D. So we substitute that value in the equation. Again, we have theta prime D equals to positive 16.667. So we can compute MDC here, which is negative 75 kilonewton meter. Now that is negative, so therefore this has a clockwise rotation. Now for MDA, we have positive 50 kilonewton meter, and that is positive, therefore this has a rotation of clockwise direction. Okay, so that is MDA. So we have now computed the member end moments. We have MDC, MDA, and we have also the MDE, which is 25, okay? And all the moment on the hinge supports are 0. So since we have now this value, so we can now compute for the reaction. So for the reaction, we compute first RCY. Okay, so we can isolate member CD. This is our D. Okay, and at D, we have here the RDL, and we have here the RCY, and the length is 4 meters. Now, we have computed MDC here. MDC is 75 kilonewton meter, which rotates in clockwise direction. So we have here the MDC, which is 75 kilonewton meters. Okay, so we can sum up moment at D. So we have summation moment at D is equal to 0. Counterclockwise moment are positive. So we have negative 75 plus 50 times 4 times 2. Then we have minus RCY times 4, and this equals to 0. And this would give us RCY equals to 81.25 kilonewton. So we have here 81.25 kilonewton. Okay, so we can compute RCX here by just simply, since you have two ways in computing for the other reactions. You can isolate dA, but to expedite the process, I would use the whole frame system. I could sum up moment at A here, and this equals to 0, counterclockwise positive. So we have negative RCX times 3, okay? Then minus RCY times 4, then plus 50 times, we have 5, the entire length of 50 kilonewton per meter, and then the distance from the centroid, or the center of our resultant, is, we know if this is 1, so therefore we have 1.5 here. So therefore we have multiply 1.5, and we also have 75 kilonewton at B, so we have a plus 75 times 1, and this equals to 0. Now we have the value of RCY here, which is equal to 81.25. So therefore we can compute RCX is equal to 41.667 kilonewton. So we have now RCX here, which is 41.667. And the remaining unknowns here is R, AY, and we have D. That is our R, AX. So we can compute R, AY here by just summing up forces vertical. So we have summation of forces vertical is equal to 0. Upward forces are positive. So we have R, CY plus R, AY minus, we have 50 times 5, and this equals to 0. RCY here is 81.25 plus RAY minus 50 times 5, and this equals to 0. So RAY is equal to 168.75 kilonewton. So we have RAY here, which is 168.75 kilonewton. For RAX, so we can just sum up forces horizontal. So we have summation of forces horizontal is equal to 0. Forces to the right are positive, so we have RCX plus RAX minus 75 equals to 0. So we have 41.667 plus RAX minus 75 equals to 0. So we have RAX, which is equal to 33.333 kilonewton. So we have 33.333 kilonewton for RAX. So these are the reactions of our frame structure. Again, guys, we do not have moment reaction here because we have only hinged external supports. And that ends our lesson on slope deflection method. So should you have any questions, you can comment it down and I'll try my best to answer your questions. Thank you guys for listening. I hope that you have learned a lot. And please don't forget to subscribe to my channel and hit the notification bell for more updates. Thank you guys and God bless.